Hey, Muso here. In this video, I'm going to be covering Atwood machines. And Atwood machines is a fancy term for an experimental setup dealing with pulleys. Let me draw a few, and then I'm going to erase all of them and only deal with one example at a time. But we have more or less. I think I'm going to go through three. I'm going to do a basic example where I have an object, two different objects attached to a pulley system. We'll say this is M1 and this is M2, and I'm going to want to figure out its overall acceleration. So it's going to be accelerating one way or the other. Okay. I'm going to do a classic lab bench style. You'll probably see this in the experimental setting in your class, where we have an object that's going to be attached to a rope that's going to be put on a pulley, and then there's going to be another object hanging down. Okay. And so it's going to be frictionless, so I didn't mean to draw that. Ignore that. And so the whole thing's going to kind of like that. And then I'm going to go all crazy on us. I'm going to put one up at an angle here. So this is an inclined plane. Really similar as all. They're all really similar, but this one we will be going up this incline or down this incline. It really depends on some factors here. But either way, the whole thing will be accelerating like so. Okay, so these are the three examples I'm probably going to get to, I think, in this video. If I run out of time, I might just cut it and do one at a time. We'll see. So let's just kind of go right back to it here. And I'm going to go and say, I've got myself a pulley, right? And I'm going to put a rope on here. I am not the best artist in the world. This is a really ugly looking machine. I'm going to say this is a 6 kilogram object. This is a 3 kilogram object, right? Now they're both getting pulled down under the influence of gravity, right? But they're not both going to fall down. There's a rope here hooking them together, so it's probably going to, since they're unequal masses, we're probably going to get a situation where it's going to something like this. One of them is going to win, right? I bet you that 6 kilograms is going to win. And I think I'll probably, let's just do this. A few things here to understand. First, the pulley won't have any effect on its inertial properties, okay? It's just a thing for the string to be connected to. The string itself will have no effect. It's small enough that we won't worry about the effect coming from the rope. Now, in real life, if we had a large enough rope on here, we could have areas where the tension in the rope was not even, and the mass comes into play. We're not dealing with any of that, okay? And I am going to ignore any effects of friction, okay? And so I think the first thing you need to understand, and this is the case with all Atwood problems, not just this particular one, is you need to assign a direction for positive. And you might think, well, down is always negative and up is always positive. Well, it gets hairy here. You can't really do that because it's actually one system. And if one's going down, the other one's going up, they're kind of going in the same direction, but they're not really, right? So what we do, at least what I do, and some teachers teach it differently, I want to look at my pulley, and I want to assign clockwise versus counterclockwise as positive or negative. And I like to pick the side that I think will win, and I think this will win. So I think the whole thing's going to do this. Okay? That means I'm going to treat everything over here as positive because it's going down. It's in the same direction that I'm assigning. And I'm going to treat everything up over here as positive. Now, I don't need to write this down, but for the sake of this video, I'm going to say on this side, down is positive. And on this side, up is positive. It's because the whole unit is moving together, and I'm saying it's all going to travel clockwise. Now, if I was wrong at the end, I would just get a negative value for my acceleration. That means it just accelerated opposite of what I defined as positive. Recognize that if I were to kind of put in forces here, this sucker has a force due to gravity like so. There's a rope stopping it from being in pure free fall, so there's a tension pulling up like so. Attention, if this is actually falling down, this tension is clearly going to be less than the weight, or else it wouldn't be accelerating. We have a force due to gravity. I'm going to have to say this FG is different than this FG, so I'll call this FG2 because it's on the right side. Why not? This one has a force due to gravity down as well, and there's also a tension up. Now first, are these tensions different? Is this rope pulling any different than this rope? No, it's all connected, so it's the same tension, okay? Got it? It's just how we're going to go ahead and define our dynamics that'll make things a little different. And so what we need to do is we need to apply Newton's second law for both objects separate from each other. What I want you to understand is that for object 1, it is indeed accelerating, okay? And we're treating up as positive, so I'm going to say it's accelerating up. I'm going to say that's equal to t minus m1g. I'm going to leave this as this. Now, I'm going to actually put t by itself. I'm going to say t is equal to ma plus m1g. Now, I'm going to apply Newton's second law for the other object, as if this first one didn't exist. And here's where it starts to get a little awkward, because remember, I'm treating down as positive. So it's still going to be accelerating positively, because now it's down. But tension is going to be negative, and Fg is going to be positive. So I'm going to say m2g, that's the positive value, minus t. So far, so good? Might as well put t by itself, too, just so I can point something out. So I'm going to do that. So it's going to be m2g minus ma. I added the t over, and then I subtracted the ma over. Well, I should subscript my masses. Yep, so this is a 2, this is a 2, this is a 1, this is a 1 up here. I don't know why I didn't do that. I'm isolating them separate from each other. So this is the mass of object 1 up top, and this is object 2 down here. Now, if you look at it, I've got a tension variable that's an unknown variable in both equations, and I have an acceleration variable, or I'm sorry, a tension that's unknown in both, and an acceleration that's unknown in both. However, I can do some system of equations, and I can take this and replace it for t up here. And that's what I'm going to do. I'm going to take this entire term and replace it for this t up here. So I'm going to rewrite that. I'm going to say m2g minus m2a is equal to m1a plus m1g. Now these accelerations are the same. I mean, think about it. Can this one be accelerating at a greater rate than this one? No, that would imply that the rope kind of got broken. They have to accelerate together. The whole system is accelerating at the same rate. I'm looking for a, so I'm gonna get a by itself. I'm gonna add the m2a term over, divide the m1g term over, and then I'll rewrite it that way. So I'm gonna say, or not divide, subtract. So I'm gonna say m2g minus m1g is equal to m1a plus m2a. See what I did there? I added that over, subtracted that over. Now, since these masses are all not the same, I can't cancel them out. I could have been a kind person and done that for you, but I didn't. But what I can do is that since a is a common term over here, I can pull a out and rewrite this side as a times quantity m1 plus m2. I'm going to rewrite this term over here. Again, I just took that common term out. Now I can divide this entire term over here and have a by itself. So a is going to equal m2g minus m1g divided by the quantity of m1 plus m2. I'm not going to put negative in for g because I've already accounted for directional information up here in my equation. So I'm just plugging in my values at this point. So m2 is the 6 kilograms. I'm going to do 6. I'm going to keep sticking with g as 10. So 6 times 10 minus 3 times 10 divided by 6 plus 3, right? So divided by 9. So I have 60 minus 30 divided by 9. Might as well put it in there. 60 minus 30 divided by 9. So 60 minus 30 is 30, divided that by 9. Whoa. 30 divided by 9 is, I'm going to get an acceleration of about 3 1/3 meters per second squared. Right on. Does that make sense? Don't make these harder than you need to. Just define a direction at the very beginning. I think that's the hardest step. And then applying Newton's second law from each other and remembering that, you know, on this side we treated up as positive, this side we treated down as positive. I could have flipped it if I had treated this side, if I had said up was positive over here and down was positive over here, then my dynamics would have looked slightly different. I would have had positives and negatives switched around. I just would have gotten a negative answer here. Psh, not a big deal. That just means that it's accelerating in opposite the direction which I defined. So in this case, it says I'm accelerating positive 3.3 meters per second squared. I assigned down as positive, so that means this guy is accelerating down at 3.3 meters per second squared. This guy is accelerating up at 3.3 meters per second squared. Does that make sense? I hope so. I know Atwood's machines can be kind of challenging. So I'm already at the 10-minute mark, right? So I'm going to go ahead and stop the video here, and I'm going to do another example, lab bench style. Cool. Thank you.